PN junction diode. Let's see how PN junction diodes are constructed. So a p-type semiconductor is taken which has extra holes, we know that, and an n-type semiconductor is taken which has extra electrons. Then we combine them together and we can see that we find a junction in between p-type and n-type semiconductor which are joined together. And at this junction, the holes from the p-type and the electrons from the n-type would try to combine because they attract each other. Holes are positively charged and electrons are negatively charged. And when that happens, we will find at the junction there are no extra holes or electrons, and that region is called as depletion region. Now we can see that the n-type semiconductor lost some of the electrons and the p-type semiconductor lost holes, and therefore on the n-type semiconductor at the junction we can see there is a positive charge because it lost the electrons, and on the p-type semiconductor at the junction we can see negative electrons because negative charge because it lost some holes. Now because of this negative and positive at the junction, we have got a potential barrier at the junction. So we have got kind of a voltage or electrical field at the junction, and this potential barrier would not allow any further movement of electrons and holes across the junction. And that's how we create a PN junction diode. Let's look at the circuit symbol for a diode. So that's a circuit symbol for a diode which is represented by a triangle and a long line. And in order to know which one is P and which one is N, we can compare it with the diode construction diagram. So the triangle is representing the P type and the long line is representing the N type. And we can quickly see how it is connected in forward bias. So that's the connection for the forward bias circuit, and that's the connection for the reverse bias circuit. We can see that the N type is connected to the positive of the battery, and that's why it is the reverse bias. Let's analyze the IV graph for a diode. So here we can see a graph plotted for current against voltage. Voltage is on the x-axis and current is on the y-axis. For the negative voltage, when the voltage applied across the diode is negative, we say that the diode is reverse biased. And we can see a very tiny current of the order of 10 to the power of negative 11 ampere for a silicon diode will be flowing through the diode. But because it's very tiny, we take it as negligible current flowing through the diode. When there is a positive voltage applied, we can see that the current starts increasing. And when it crosses the knee voltage, which is around 0.7 volt for a silicon diode, we can see that there is a huge forward current flowing through the diode. This knee voltage is also called as threshold voltage. But we can see from the plot of the forward bias characteristics that the current versus voltage graph is not following Ohm's law because we don't get a straight line passing through the origin. So diode is a non-ohmic conductor.